So welcome everyone to another Brandeis Mersex seminar. Hope everyone is doing well. Just a couple things, right? So everyone will be muted as you enter, but you're welcome to unmute yourself and ask questions so you don't leave Jeremy talking to his computer all the time for a whole hour, right? The other way you could ask questions if you don't want to jump in is you can just type in chat or raise your hand and I can, help with that. Then I can read your question in chat or, call on you and you can ask a question. Then, of course, we'll have a little bit of discussion at the end too. So if you have some sort of, more detailed question or something, you're welcome to wait until the end. But, really, I encourage you to ask questions so we can have some back and forth. And yeah, so thanks for showing up again. And, it's really, really a pleasure to introduce Jeremy Polacci, who's coming to us from UC San Diego, where he's an assistant professor there in physics. He has a, really long background in colloids and soft science. He did his undergrad and grad work in France in Lyon, right? And then moved to New York to join our friends in the Chaikin lab at NYU. And then of course he moved off to California. So, I think he has some really interesting work about, building active matter from the ground up using synthetic materials, right? Something that, we sort of cheat with at Brandeis often by, taking active matter from things that are already doing active matter. This is, without any further ado, Jeremy, please go ahead.
Thank you, John, and thank you for having me virtually. One question before I start, can you see my pointer? I should have checked before. Can you see my pointer?
I can see your mouse, yeah.
You can? You
yes,
can see it, okay.
Can.
So I will use it during the talk. Very importantly, feel free to stop me at any point. And I can't see your faces, so just like interrupt talk and I will stop talking to leave you the floor. And so what I want to tell you today is about like non-equilibrium pathways for self-assembly. That's the work we've been doing since I moved to San Diego. And I was told by Seth and John to preparing this talk that part of the MERSEC was a very, I would say, large and broad group of people in biology, chemistry. And so I will start with like a very basic motivation of soft matter, like try to give a sense of what is soft matter. So I know Brandeis has a long history of soft matter, but I will doing so by kind of emphasizing aspects of soft matter which will legitimate and I would say explain or give a hint of what we're doing, what we do in my group. So soft matter or soft condensed matter is a branch of condensed matter physics. And like its older cousin, condensed matter, it's interested in emergent properties from many body systems interaction. So soft matter is ubiquitous in our daily life, in food, so mayonnaise and paste. It's also an essential, liquid crystals are an essential component of soft matter. So we see they're everywhere in our lives, and so they're liquid crystals everywhere in our cell phone screen, which themselves took over our lives. And now I would like to briefly introduce an example I borrowed from Degen, which really gonna emphasize some crucial aspects of soft matter that will explain how we spin active matter in my group. So if you take like the sap of an EV tree, so you take a tree, you make a cut, and then it's gonna bleed or just like exit some sap. So the sap is a gooey.
Jeremy?
Yes.
We're still seeing your title slide. Is that what we mean, what we are meant to see?
No, you're right. I didn't change. You're absolutely right. Thank you. Now you should have the right one. So sorry. So that was I was mixing up my presenter and the other one. So that was the mayonnaise, that the liquid crystals, they are part of soft matter. And now I will discuss the case of rubber or like sap. It's an example I borrowed from Degen. So if you take like an EV tree and you make a cut, it's going to start bleeding like a gooey liquid, sap. And so it's a liquid made of solvent, like water, principally, and long polymer chains. And you can see that when it's bleeding from the tree, you have like this non-Newtonian fluid as an effect of the presence of those long chains of polymers inside the liquid. So if you now get this sap into a bucket and you leave it in presence of oxygen for a few minutes, the oxygen will react chemically with some of those, I would say, long polymers in solution, which will bridge. And so now, all of a sudden, instead of having a liquid with long chains, you end up with a liquid enclosed in a network. And so instead of having a gooey and viscous liquid, now you have an elastic solid, which is rubber. And so that highlights two essential components of soft matter. First, it's going to make it's going to go under drastic changes with mild modification. So here you have a chemical reaction which can happen at room temperature, and that's enough to turn the polymer chain into a network. And importantly, instead of having molecules, you replace, you add it to your system an intermediate scale, which is a mesoscopic scale, where those different chains would form a network, and that's essential to soft matter. So what I will use in just 1 second, it means that soft matter has two components. One is that the interaction is of the order of kT, and the other one is that there is a mesoscopic scale between 100 nanometers and a few microns inside the system. And I will show you in just 1 second how we can understand why soft matter is soft just from this argument. One last thing on the EV3, that's actually the way Native Americans were making boots before the rise of the polymer industry. They would take the sap, they would let it flow in a bucket on their foot. They would, on a bucket, they would dip their foot in the bucket, let it oxidize, and then you would reticulate and become this solid rubber. They would remove their feet and they would have rubber boots this way, well before the advance of polymer chemistry. So now what I want to show you is like this very, I would say, basic view of soft matter as just like a collection of a particle with or interaction kT and a mesoscopic scale is sufficient to understand the delineation between what is hard and what is soft materials. So if you ask a mechanical engineer or somebody who is maybe not, I would say, versed in physics, what is soft and what is hard, they would just take the material and push it with their finger. And based on the response, they would say this is a hard material or this is a soft material. From a more, I would say, formal point of view, when you do this experiment, what you're measuring is a Young modulus, which is the deformation of your object as a result of an applied pressure. So the Young modulus is it's units of pressure, and therefore it's a force per unit of area or an energy per unit of volume. So you can make a dimensional argument, which was originally made by De Gennes as well, that the Young modulus of a material is given by the density of energy in that material. So if I know the typical interaction between the building blocks and the average volume taken by those building blocks, I can compute the Young modulus. So if I make this argument, for example, for a piece of iron, and I say that it's a BCC lattice, which it's not, but just for the sake of the argument, the typical interaction between metal atoms is going to be electrostatic, is going to be of order 1 electron volt. Now, if I look at what is the volume of the BCC lattice, is going to be A cube, with A is atom to atom distance. So I can just argue that the Young modulus of iron is going to be of the order of 1 electron volt divided by 1 nanometer cube, which gives you 1 gigapascal, which is the Young modulus of a metal. So now if I consider the situation I just discussed for the sap, where the building blocks are like 1 micron and the typical interaction is kBt. So I can now look at the Young modulus and say that the interaction is going to be kBt. So kBt is 1/40 of an electron volt. You can remember that as an order of magnitude. But most importantly, instead of having 1 nanometer cube, you now have 1 micron cube. So you can see that your volume has increased by a factor of 10 to the 9. And so as a consequence, you end up with a Young modulus, which is going to be of the order of a Pascal, which is very soft. And so we can see that this very simple argument saying that particles have an interaction of order kT and over a mesoscopic scale is really essential to explain why soft matter is soft. And so what we're doing in my group is start with this premise and ask what happens if we do soft matter with an active twist. So let's say, we know that soft matter is going to be defined by this mesoscopic length scale and that type of interaction. And the question we're asking is, what happens if some of those building blocks are special, and special will be defined further in the talk in different ways. It's special in such a way that it can inject energy. And so the question we're asking is, how can one change soft matter by pouring it from within? And so what I will show you is how we can steer, control, or self-assemble matter and soft matter using synthetic particles. So when you ask this question of like what's happening when you power soft matter from within, you're basically funding the field of active matter. And there's been a lot of work in the last decade or so on the field, which was primarily focused on the emergence of collective behavior and broken symmetries in collections of active particles. So here, for example, you can see the formation of flux in a collection of rollers in the group of Denis Barthelot. There's obviously the work I think you're all familiar with by Zvonimir, where you use active matter from biological system, but in different use them as building blocks. And here you can see a vesicles, which is powered from active nematic on its surface, or worked we've done almost 10 years ago with Paul Chekin's group, where you could see that you would get like phase separation as a result of persistent motion. However, I would argue that, However, I would argue that even though like most of those examples really focused on looking at broken symmetry and the emergence of mesoscopic flux in collections of active particles, we didn't really tackle another aspect of the powering soft matter, which is the self-assembly. By observing nature, we know that the fact that particles consume energy allows biology and natural system to evolve and to self-organize in exquisite ways. So here, for example, you can see the embryogenesis of Drosophila from Streichen lab at UCSB, or if you look at the foot of a diving beetle, you can see it's like extremely well organized, and just like it's a level of self-assembly which is like far ahead of what we can do synthetically. And one of the way nature can do that is by using active building blocks, which will consume fuel and to some extent allow to overcome the entropy bottleneck that you have in an equilibrium system. And so what I will show you in the following is how can we do active matter? How can we use synthetic building blocks, power them, and get them to self-assemble in a system with a level of organization which has not been reached previously in synthetic system, in synthetic and passive system. And beyond that, they will also offer an opportunity that you cannot have in equilibrium, which is that systems of active particles can be dynamic, while passive system can be as complex as you want, but they're obviously steady and completely static. So to answer that question and show you what we've done to tackle those questions, I will show you a tale of two stories on how we can use active particles to control colloidal crystallization of passive spheres, and on the other end, build micro machines. So if you ask yourself, how do you control a system by powering it from within? The most simple experiment you can think of is what is the effect of energy injecting from within on the crystallization behavior of microscopic colloid spheres. And so that's the experiment we did with Sophie Ramanarivo, who is now a faculty at LADIX when she was a postdoc in my lab, and with Etienne Ducrot at NYU, who is now a faculty at CNRS in Bordeaux. So we, in order to do this experiment, we wanted to study 2D monolayers of passive spheres and add some active particle and see how the activity would change dynamics of crystallization. So those are passive sphere. We use like 5 micron silica beads. They're relatively heavy, so they fall near the substrate and they stay there. So we have a quasi 2D system. And they're 5 microns, which they're large enough that they can easily be observed. And they're not so large that there's no thermal motion. So we can see that they're moving a little bit, but they're not very fast in their diffusion because they're fairly large. The active particle we're using are active particle we developed a few years ago while working with Paul Cekin at NYU and Stefano Sacana. So they're like light activated particles where an inclusion of hematite, which is a photocatalytic material embedded in a polymer sphere, can be actuated by light. So that's what you see here. If you put those particles, they're heavy, they sediment near the bottom substrate. And if you shine the light, they do a persistent random walk, which means that they self-propel with a speed of typically 13 microns per second and make change direction every 2 seconds, which is set by Stockenstein rotational diffusion. And that's the behavior we can see. So you can see this persistent random walk is very different from thermal Brownian motion, for example. So to give you a sense of the experiment, we take the 5 micron sphere, we prepare a suspension of them, and then we let them sediment. And what happens is they sediment near the substrate, and if the density, the surface fraction is large enough, they start crystallizing. But obviously, crystallites won't be all alive at once. So what you observe is exactly what you see on this picture, which would be like something like 400 microns. Those are 5 micron particles. You can see that you form crystallites with a good orientational alignment, separated by grain boundaries because this crystallite is not aligned with that one or that one. And so what's going to happen is the crystal, the single crystal is thermodynamic ground state, and this system will slowly age in such a way that is going to lead to one large crystal. So I will try to be careful during my presentation to differentiate between thermal and equilibrium. So here the system is not, when the system is not injected with energy, it's a thermal system, it's not an equilibrium system because it's still an evolving system. So I will oppose a system with no injection of energy beyond thermal fluctuation and a system where fluctuations which are non-thermal are injected. Once again, if you have any question, just interrupt me. So this is the experiment. I will start the movie just to give you a better understanding. So we take those 5 micron sphere, we let them sediment in arenas, microfluidic arenas, which are hexagonal that assist the crystallization. And on the left side, we have those particles in an arena, and we have something like, so we have 5,000 passive sphere with roughly 1% of active spheres. So we change the surface fraction, but we typically have like something like 20 to 60 active particles in 5,000 passive. The right side is the same experiment. I mean, is an equivalent experiment where we have 5,000 passive sphere in an arena, with active particle, with the one difference that we won't turn on the light. So the active particle will actually never be activated. They will just remain passive. So this system is completely passive and thermal, while this system will be active. And so now I will show you what happened when we turn on the light. So at first, let's look at the thermal case. So you see very little happens. So now it's sped up 10 times. And if you speed up even 300 times, you see that there's barely any change. within the course of this experiment. So like this movie is 45 minutes. So the bottom line is if we take this system and let it evolve over 40 minutes, we barely see any change. We initially started with a variety of grains of crystal separated by grain boundaries. And after 45 minutes, we have some change, like a few of those grain change, but we still have a bunch of crystallites separated by grain boundaries. Now that we agree that nothing happens or not much happened on the thermal side, let's look at what happened on the activated side. So I restart the movie. And so now you see that it's very different. It's a much more dynamics, and actually we can see streaks. Those streaks in the crystal are a result of the propulsion of the active particles. So you see it's only a few of them. And once we speed up 300 times, we see that after like 30 minutes or so, we converted our whole polycrystallite in one large crystal. So I'm going to replay the movie one time so that you can really look at it. So we can see the streaks. You see there's very few active particles. Indeed, like maybe 20 for 4,000 passive particles. So like 0.5%, it's like kind of doping. And very quickly, we converted our polycrystallite in one large crystal. So to make it...
Will it, the thermal state be wind up in the same final state as the active?
Sorry?
If I wait long enough, if I wait a year,
yes,
the thermal state.
Absolutely. So yes, sorry. Thank you for. So I have one small question. Can you tell me who you are when you ask the question, because I can't see your. But so to answer the question, it's absolutely right. As I said before, you have those polycrystallites. The thermodynamic ground state is one large crystal. So if you wait long enough, it's going to happen. So in the thermal state, it's going to take something like 12 hours. For the system to, in our conditions, with that system of that size, we get a large monocrystal after 12 hours in thermal condition, and after 40 minutes or so, 30 to 40 minutes in the activated state. Thank you for asking the question. And so to quantify the quality of our crystal, we look at the bond order parameter. So what we can see is that locally, if you look at the amplitude of the bond order parameter, you see that locally you have a good crystalline hexagonal order. So it's like something which is a crystal, but you see that at the grain boundary, you don't have that quality. On the other hand, if you look at the orientation, you can clearly see the different orientation for the crystallites. So in our experiment, we see that we start from something which has many different orientation of crystals that convert after 40 minutes in one large crystal. So in order to quantify that, we look at the bond orientational correlation function, which is the correlation of the bond order parameter. And it allows us to compute the correlation of this parameter. So it's the typical size of how the correlation decay in the crystal. So we can see if we plot G6 as a function of time, we see that G6 is increasing as a function of time. So the system gets more correlated, which makes sense because it becomes a single crystal. So we define a typical size of a crystal, such as G6 of R6 is 1/2. Okay, and so we said that when it's below 1/2, we lost too much correlation to say that that's the same crystal. And so that allows us, R6 is, we obtain from this value is a typical size of the crystal. So we draw this line, and we can, for different time, and we can get like what is the value of R6 cutting 1/2. Okay, so on that regard, this value of 1/2 is arbitrary. We just need a value which is high enough to actually have some sense in the sense that we're still in the same crystal. So we try 1/3 or 1/2 or 2/3, it makes zero difference. If you take very small value for the cutoff, then you end up with being dominated by noise. If you take G6 has to be equal to 1, then it's only true if the whole system is converted and you have finite size issue. So that's like we took 1/2, but we made sure that this result I'm going to discuss in a second are not depending on that parameter. Okay, so from this graph, which is experimental, we can compute R6 as a function of time. So R6 as a function of time is the value of R6 over each one of these curves. So if we compare the thermal case, which are the black dots with the activated case, which are the colorful symbols, you see that R6 is increasing a lot slower in the thermal case than in the activated case. Okay, and that's basically what we just saw qualitatively, which is that it takes a lot less time for the system to anneal into one large crystal with activation than without activation. And back to your question, it would take up to 12 hours for the black lines to reach the value. And so now, in order to quantify those curves, we looked into grain growth, and there's just for thermal systems which are aging, there's a large body of work arguing what is the power law of you should use during the grain growth. So we decided to go for the most simple description of the grain growth, which is a normal grain growth, which is curvature driven. So we end up with dr over dt is gamma over r, and gamma is the grain mobility. So we could qualitatively describe our experiment with this normal grain growth, which gives you R6 is going to go like the square root of time. And so from the dashed line, we could extract the grain mobility. And what we see is that the grain mobility is 40 times larger in the case of activated monolayers than in the case of thermal monolayers. And so the question was, what's happening? What is driving this increase of grain mobility? So in order to do that, we step back and we look at the microscopic properties of our system and what were the effects of the swimmers in the monolayer. So if you look at the trajectories of the swimmer in the monolayer, what you see is that they tend to follow the direction of the crystal. And so we see that they, on average, like only follow those directions. Okay, and that's what you can see in the trajectory. A simple argument for that is just much easier to unzip a crystal than to actually push head front, which would generate a full disinclination, which just requires too much energy. Something I didn't say so far is that the surface density in the experiment is 0.68. So it's not super, I mean, it's a crystalline monolayer, but it's not super dense. There's still a little bit of room to reorganize. Okay. So the next thing we did with the monolayer is to look at what is the average distribution of statistic of the microswimmer in the bath. Sorry, in the crystal. So the reason for that is that initially when we did the experiment, we look at the trajectory of the microswimmers, and we decided to try to see how those microswimmers would interact with the grain boundary and the rest of the monolayer. But it ended up like excruciatingly difficult because you would have to account for like the inclination with the grain boundary, and it was very hard to repeat the experiment, and every grain boundary would interact with other grain boundaries. So it was just very difficult to get anything quantitative and reliable. So on the other hand, if you look at the uniform distribution of active particles in the system, what I want you to get from this figure is that it's fairly uniform. So there's a tiny bit added accumulation of the active particle at the boundaries, but it's more or less very uniform. And that's something which is very important for two reasons, because if we see that on average the active particle spends the same amount of time everywhere in the monolayer, then we can step back and say, okay, let's do a mean field approach where we don't look at each microswimmer individually, but we just consider them as a bath. Okay. And I would also like to make a tangent at this point to stress why nobody did this experiment, and we could do it here, because really this question of what is happening when you're injecting energy in a monolayer or in a polycrystal is arguably the simplest, most straightforward question anyone who's interested in statistical mechanics of active system would ask. And the reason why it was actually a difficult experiment is, let's imagine you take active particle and passive particle. So you put a few active particles in passive one. So it's been shown by Aparna and Michael Hagen at Brandeis and others that if you mix particle with different mobility or motility, you end up with a phase separation. So what you would end up with is that the active particle would push away the passive one, and you would basically demix. And so as a consequence, your activity separates from your passive particles. So in order to avoid this demixture, one thing you can do is to put boundaries, and then you confine your system to make sure that the active ones cannot push the passive ones. And if you do so, you have this other thing happening, that particle with persistence random walk, so basically active particle which move in straight line and then make turns, tend to accumulate at boundaries. The reason for that is because they run, then they reach a wall, and then they slide along the wall. So if you confine active particle, after a transient, you will end up with all the active particles near the boundaries. Once again, you phase separated the activity from the rest of the passive monolayer, and therefore you cannot do the experiment. So what Sophie did in the experiment was a very, I think, like nifty trick, experimental trick. So she confined the particle in an hexagonal arena, because otherwise passive particle just escape. But she confined them in an arena which was shallow enough and with slanted walls. So the slanted walls allow the active particles to escape and to come in, but the presence of walls on the other end doesn't allow the passive ones to escape. So the passive particles are confined, but the active ones are basically in an infinite bath of infinite reservoir of active particle. And by doing so, we can ensure that the amount of active particle remain constant through the course of the experiment. And that's what shows this picture. And that allows us to say, okay, let's step back and take a mean field approach. So now that we, take this mean field approach, we can say, okay, let's forget for a second about the active particle and look at the passive ones. So if we look at the displacement of the passive particle as a function of time, so we can plot their mean square displacement as a function of time for different conditions. So the black symbols are the thermal case. We see that delta R square is linear with time. We have a diffusive displacement of the particle, and we can estimate the diffusivity of the 5 micron particle. What we see is that even in the presence of active particle, delta R squared at long times for like a few minutes is linear with time. So that tells us that we can extract an effective diffusion coefficient from the dynamics of the passive beads as a result of the presence of active microparticles in the monolayer. So here I plot df as a function of the properties of the active intruders, which are their speed or their numbers. So alpha is typically from 0.3 to 2% in numbers compared to the passive ones. And df is gotten from the fit of those curves with a linear fit. So what we see is that the faster the active particles, the higher their effective diffusivity, the more of them, the higher the effective diffusivity. Can we understand that? Let's try to see what actually happens. So here, the figure on the top left is an actual picture of the experiment where the color of the big spheres is a reflection of their displacements. So you can see that all the blue particles basically didn't move. The red particle is the active one, and we can see that it's moving by unzipping the crystal, and most of the displacement is transverse. Okay, that's what you can see here. So now we can say that what is the collision rate of the passive bead with a particle? The collision rate is going to be proportional to the number of swimmers times the cross section, which is going to be the speed of the swimmers times the interaction range, the transverse interaction range. Now, if we
ask a very quick question.
Yes.
Please. So I'm just curious, are the active beads the same size as the passive ones?
So now, so I mean, that's, sorry, is that something maybe I didn't? So the passive one are 5 microns. The active one here are like 1.5 to 2 microns. So this is really a picture. So it's at scale. And so you can see that the active particles are smaller. There are some practical, it's very hard. If you put an active particle which is as big as a passive one, it's very hard to move without making a disclination. And disclination are just so costly that they don't happen. So we had to, another thing you have to think when you do the experiment is here, it's actually not 2D, it's quasi 2D, they are spheres, okay? So if you take a very small active particle, there's actually a lot of space below the belt of the large passive one to travel without touching anyone. So you need your active particles to be large enough so that it still pushes active ones when it's moving around. And we have this caveat that if we go too big, then we need to form disclination and they just don't happen. Does it answer your question?
Yeah, that does make a lot of sense. Yeah, I was just curious because there are different like ratios of like if you have a bidispersed packing. So I was wondering if there was some special reason. But
it's an excellent question. I don't know what's happening, for example, for glass. And there's this one thing which is, I mean, because the system is quasi 2D and not actually disks, there's actually, you have to be careful that the particles don't end up just running below the belt. There's not enough space for them to run between the particles without touching them. There's a bit of space near the substrate when you stack spheres. And so we can compute.
Can I ask one more quick clarifying question? Do you still have this unzipping motion once you reach this single crystal? Or do you still have mobility of these swimmers inside, or only when you have a connected crystal?
No, you still see the unzipping, but it's just as a result of the unzipping, you don't, it zips back and then there's no, it doesn't generate defects. Like it's basically like, it's a situation where you help annealing, but you don't induce more defects once you reach the ground state.
Thank you.
Okay. So we can compute the collision rate. From that, we can compute the effective diffusivity. The effective diffusivity is going to be the typical displacement following a collision squared time the collision rate. And so there's one feature about the displacement. Because we're at low Reynolds, we don't expect this parameter to depend on the displacement following collision to depend on the speed of the active particles. So it's a constant. And so from that, we can compute that dF is going to be a prefactor depending on the displacement, the transverse interaction range, the density of swimmers, times alpha, the surface density of swimmers, times their speed. So if we go back, if we go back to our data dF, and now we plot them as a function of alpha v as our scaling would go, we see we have a very good agreement and a collapse of all our data on the master curve. Moreover, we can actually get the slope of that curve, and that would give us an estimate of D and L. And we see that D and L are basically sigma, which is the diameter of the passive bead to the fifth. So it says that we have like a displacement and a range of typically 1 micron, which is also the size of the small bead. So it's entirely dominated by steric collisions. It's like hard sphere hitting hard spheres. And we don't see any entrainment. So now we previously measured like the mobility of the grain boundary. We now computed the effective diffusivity of the passive particle that we could connect to the behavior of the active intruders. So now we can plot one, like basically gamma, which is mobility of the grain, which is a macroscopic property, as a function of dF, which is a more microscopic one. And what we see is that if we plot one against the other, they look like they fit very well an Arrhenius law. So it means that basically your particles, like the mobility of the grain is an activated process. And due to the presence of intruders, you just like have a hot bath, and that helps the activation of your process, and your mobility is increased by just an Arrhenius prefactor. So that's what we had. It was, I mean, obviously a bit disappointing, because then we could ask, okay, does it just tell us that everything we've done was equivalent to taking the box and checking it? and that seems to be the case. Just to make sure that we didn't miss something, and also because there was some literature, that was the first experiment, but there was some numerical literature, notably by the group of Gistra in the Netherlands, were saying that if you put active particles in a polycrystallite, it's going to anneal, but the annealing come from the boundaries of come from the grain boundary, which was completely different from what we've seen. So we were wondering what was different in her simulation compared to our experiment. So I turned to my friend and colleague Etienne at NYU, who was using now a CNRS, who was using LUMD at that time, which is like a Brownian dynamic simulation, which allows to put active particles, with the questions like, what happens if you simulate passive beads and you put 1% of them active? And so Etienne did a quick run of the experiment, of the simulation, and qualitatively it looked exactly like our experiment. When we would run the two movies side by side, they would be almost indistinguishable. So we decided to keep going on that direction and to see what Etienne would have in the simulation. So he ran basically numerical experiments of our experiments, and we treated them exactly like the experiment. So we just dimensioned everything the same way so that we could really compare like apple to apples. So the top panel here is the experiment, the bottom panel here is the simulation, and we see that we have a reasonably qualitative, quantitative agreement between the two. Even here, like, sorry, this one here, those are like real number, here are dimensionless, and this panel is everything is put on the same dimensionless quantities. But we have a good agreement between the two, and we also see this Arrhenius law. Now, if you plot gamma, the mobility in dimensionless units, both in the experiment and in the simulation, we see that we have a really good agreement between the two. So the only difference between those two curves is the height of the energy barrier in the Arrhenius law, where in the experiment it's I think 5 kT, which is also reasonable for something which would be like of entropic origin, and in the simulation I think it's a factor of 2 from that. But we didn't try to adjust, to fine-tune the experiment so that they would match. We just took something which we thought was reasonable, and we show that those simulations who have no hydrodynamics, who are completely 2D, give a result which is very comparable with our experiment, which also goes in line with the fact that it seems to be dominated by contact. So the fact that they are not phoretic particles in the simulation, the fact that we didn't put any fluid is not an issue, and that's confirmed by those experiments. Still, what Etienne was saying was particles going everywhere, and not at all what Gistra would observe, which was that particle would all active particle would colocalize at the grain boundary and then anneal from there. So then we could do, now that we validated the simulation, we could do something in the simulation that we would not be able to do in the experiment, which is namely varying the persistent time of the particles, keeping the speed the same. So here I'm going to show you two simulations where the active particles are the black dots. They're just like bigger so that we can see them more easily. And the speed is constant. What is different on those two panels is on the left panel, the persistent length of the active particle is like seven times the size of the passive particle. So it's like high persistence. That's more or less the experiment. And on the right panel is going to be a simulation where the persistent time is set such as the persistent length of the active particle is a fraction of the passive particles forming the background. And now I'm going to run the movie. So you see the particle run around. And at some point, we're going to accelerate the movie so we speed up the movie. And what you see that on the left panel, the particles, the active particle remain like everywhere. They travel everywhere. While on the right panel, at short persistence, we see that all the active particles, they colocalize at the grain boundary. And from there, they melt
quick clarification, Jeremy.
Yes. Yes, Aparna.
In the simulation also, you have the size ratio that is the same as in your experimental case where it
Yes.
was like 1:5.
Mhm.
Okay, thank you.
Yes. Yes, we use the same. This issue of disclination, you have that in the if you set the force and not the velocity, if the amount of if the amount of force you need to move to make a disclination is too high, you just stall. So that we would see that as well. Okay.
Perfect.
And sorry, back to so on the left panel you see that they travel in bulk, while on the right panel you see that they colocalize near the grain boundaries. And so the mechanism for annealing is drastically different between the two. One way we can understand, and so that's the reason we had a different result from GSTRA. There's actually something which was not mentioned in the paper, but in their situation, their simulation were made in a short persistence regime. And if you have active particle with short persistence, then you end up with like effective attraction between those active particles. What's happening is they're colliding with the passive, they're making a bubble, and they end up being attracted to each other. So that was something that there was a paper by Brenner a few years ago who mentioned how you could end up with effective attraction between active particle at low persistence. And I think that's more or less what we see that. And so now if we measure like the effective diffusivity of the passive particles as a function of the persistent length of the active, what we see is we go from a plateau at short persistence to an increasing one. And so what we see here is a dynamic transition in the way we transfer energy from the active particle to the bath as a function of the persistence of the active particles. And that is something that you never get in a passive system. So when we saw that gamma was a function, gamma tilde was conveniently described by an Arrhenius law, it hopefully looked like our system is well described by an effective temperature. You just shake the box. What we unveil here is that it's a lot more subtle because the mechanism by which you anneal is driven by the persistent length of the active particle, and this has no equilibrium counterpart. And from that, we can also experimentally play a little bit. Now that we know we can control the activity with light, we can take a system and shine the light on one side and not on the other side. And what we see is we get annealing, which is controlled in time and space with a resolution of a few microns. And so here you see like the effective diffusivity, and you can clearly see the separation between the activated state and the non-activated state. So why should we care? Is because thermal treatment is really at the essence of all thing metallurgy, and we know that we can control the behavior of a system by using its thermal treatment. So we know we can use that in an equilibrium, in a macroscopic way. And the question now is, what can we get from a quench which can be controlled in time and space with a few micron and a second or a few hundred of millisecond resolution? So how can we control our system by using active noise? And I think that's an interesting question that we are now working on. So I'm done with that part. I run way over time, so I will still like to present the second part. If you want to ask questions, I can answer them now, or should I move on to the second part? So there's no opposition. Yes.
Yeah,
I
you're
want to
welcome
hear the
move
second
on.
part.
Yes, please move
Okay.
on.
So I'm gonna move on. So that was, I mean, I think the first part was more about, like I would say, statistical mechanics of injection. How can we control a system from injection of energy from within? And now I will like to discuss how you can actually get active particle to self-organize and to self-assemble in small machines, or to paraphrase Leibniz and then Zvonimir, machines made of machines. And I will show you how we can build those, or how we can let the system build those small microgears. So I will need at this point to tell you a little bit more about how those particles move, because I very graciously put it under the rug at this point. They say we have active particles. I didn't say why they were moving. So the way they move is they use phoresis, which is motion in a gradient. So if you put a colloid in a gradient of concentration, it's moving by a physical phenomenon called diffusiophoresis. So now if your particle has an chemically active side and a chemically inert side, it's gonna, and you put it in a fluid, it's gonna self-generate this gradient, that's a Janus particle, and it's gonna self-propel by diffusiophoresis in the gradient it generated, and that makes active particle, and that's basically a strategy that has been used by many people in the last 20 years to get microscopic self-propelled particles. So in order to make a gradient, you need a catalytic component, and the catalytic component we use is hematite. It can break down hydrogen peroxide into oxygen and water, and it's conveniently activated by light. So it's a photocatalytic material. If you take a cube of hematite, as here, which is 500 nanometer, and you put it in a uniform concentration of hydrogen peroxide, and you shine light on it, it's going to break down hydrogen peroxide. You're going to get a steady concentration profile, like 1/R. But this particle is not going anywhere. It's not going to go anywhere because the gradient is symmetric, and it just is a sink of H2O2. So the question we asked then was, what happens if we put this particle in a gradient of light? So here we have high intensity of light, low intensity of light. The black things are hematite cubes. And what we see in this movie, which is accelerated, is that the particles, they move along the gradient. So the reason for that is that the reaction rate is a function of the light intensity. So we have a higher reaction rate on the bright side than on the dark side. And as a consequence, the particle is going to self-generate a gradient, and it can move. So I won't get into the details, but I want to show you that this picture is adequate. And we did experiments, we repeated experiments where we made different gradients of light. And we could compute, there's only two parameters in this picture, which is like the saturation light and the mobility, if you'd like. And we can predict what would be the speed of the hematite as a function of the light, the spatial gradient of light we impose, with only two parameters. We repeat the experiment. The symbols are the experiment, and the solid lines are the prediction we have for the hematite speed, with two parameters for those three curves. So bottom line, we can describe all our experimental data for different types of light gradient with only two parameters. And that shows that diffusiophoresis is really the important thing to get our particles to move. That's what I want to get through this slide. So now we have this hematite cube, and we saw that if we put it in a gradient, it's going to move. But let's attach it to a sphere. So the sphere, this polymer sphere, is inert. So we now have a particle which has an active, chemically active side and an inert side. We just remade a Janus, and it's a self-propelled particle. We know that the particles tend to travel towards a low reaction rate. So it's going to self-propel with the sphere heads on, and that's a particle. So that's what you can see here. And it's just like a variation of the particle I showed you before, where basically the cube is more extruded than previously. So why do we extrude the cube? Is what I'm going to show you in 1 second, is what happens now if we take those particles and put a gradient. So we put a laser here. So we have a light gradient. And what we see is that the particles which originally were inactivated, so there was just Brownian motion, they will all start migrating towards the bright spot, which is a laser spot. And now it seems that they're not moving, but we're actually moving the stage. So if they can stay near the laser, it's because they can continuously migrate to recapture the light spot while the stage is moving. So basically we have a particle which is phototactic. So why is it so? Is that if you put those particles, in a light gradient, they will travel, and the hematite will be steered in the light gradient, and so the particle will continuously reorient so that it travel along light gradient. So we can make a phototactic particle. So what do we do with that? So what we did was we showed that we can get those particles to self-assemble into a toy. So we start with a dilute suspension of those particles. Why do we do dilute? We do dilute because if we take too many of those particles and density is high, then they will run into each other and they will do a motility-induced phase separation, which is a completely different type of physics we didn't want to study. So we start dilute, and because all the particles travel towards the laser spot, then they will you will get local concentration, and we'll see what happens in a second. So we have those particles, we shine a laser spot, we see that they all travel towards the laser spot, and they collide, and then they break down, they make something, and then they break down. And that's really an essential feature. If you want to build a complex architecture, you have to have the right to fail and disassemble. And so it disassemble a bunch of time, but eventually it's going to form this microgear. And now that the microgear is formed, you can turn off the light gradient. You just need to keep some light, obviously, otherwise the system is in equilibrium and just like everything breaks down. But now the light is uniform and you can form those self-spinning gears. And they can stay alive or like stay stable for up to an hour. So I'm gonna replay, I'm gonna replay the movie once, because I think it's a really cool movie. So you see that all the particles, they come near the spot and then they break down and they collide and they form and then they re-break down because they didn't form the adequate structure. And then eventually they're going to form a microgear made of one particle in the center, which is flipped, and 6 at the periphery. And then the structure is stable and starts spinning. So we have zero control at this point. I mean, I will discuss you how we can have control, but at the assembly stage, we get clockwise and counterclockwise microgears completely randomly. We took like all the rushes out of 4,000 gears. We get 2,015 one way and the rest the other way. So it was completely random. So how it's happening is we have those particles which are like going towards the bright spot by phototaxi. Then one of the particles is going to flip this on the laser spot. The reason for that is that hematite is also absorbing for blue, and so if you pass above the laser light, then you have absorption. So it means that you have less light on top than on the bottom, and so the hematite tail will migrate towards the dark as it did before. So we have one particle which is now flipped, swimming downwards, and if you swim downwards and you reach a substrate, then you form a pumping monopole, and this pumping monopole is going to get the other particles. Then you'll get like a spontaneous symmetry breaking, and you end up with a self-spinning microgear. So we can control the dynamics of the spinning with intensity of the light. At high intensity of the light, the movement is persistent. At low intensity of the light, the angular speed is reduced, and the particle can have intermittent reversal of orientation, of like the statistic of which we're studying right now. I can't tell you much. And so we have this new building block. So the question is, okay, what happens for a pair of them? If you take 2 of them and bring them together, they just repel. And the reason for that is from a far field point of view, each one of these micro gear is a sink of H2O2. And at this value of pH, it's repelling for particles. So those two microgears repel each other with the phoretic repulsion, which is the gradient of the concentration, which is 1/r squared. Now, if we look at pairs of those particles, there's 2 cases. They can be co-rotating or counter-rotating. So here you have 2 co-rotating pairs. We use light patterns to force them to stay at a close vicinity, because otherwise they would just drift away. So they repel, but they cannot. So they stay at a fixed distance. And what we see is 2 co-rotating gears co-rotate at the same direction as the rotation of each gear. Now, if we take co-rotating gears, contra-rotating gears, we don't see any co-rotation, but what we see is synchronization. So you see the synchronization in just 1 second. In a stroboscopic movie set on one, we see that the other one is moving tooth by tooth. So we basically have 2 microscopic gears which are synchronized by their teeth, but they don't touch. So we have synchronization with no contact. And you can quantify the synchronization by looking at the phase lag. And you see that in the co-rotating case, there's no synchronization. In the contra-rotating case, you have a peak of the phase lag, which shows the synchronization. So then we can ask, what is the origin of this synchronization, or what is the origin of this interaction? I think the most straightforward response to that is hydrodynamics. Those things turn and therefore they make flows. Also, when you have like vortices which rotate around each other, it really screams hydrodynamics. So that was our first guess. There's one issue with that. It's a big one, that if you take one of those microgears, because of phoresis, each one of those swimmers are force-free. So we could expect that those microgear would be torque-free. So if they spin that way, it means that on average, the fluid flow has to compensate and has to go the other way. So now if I put two gears co-rotating next to each other, I indeed predict that they would co-rotate, but they would co-rotate in a direction which is opposite to the direction of their co-rotation. And that's opposite to what we see experimentally. So I'm not saying there is no hydrodynamics, I'm just saying that it cannot be the major contributor to what we observe, because it goes the opposite way and it predicts a co-rotation opposite. So if it's not hydrodynamics, what it is? So it has to be it has to do with a chemical cloud formed by each particle. So here we have a COMSOL simulation of a rotor. So it's like basically what does the concentration profile look like around a rotor? And here we solve the concentration profile in the static case. So it's Laplacian of C equals 0. The reason we can do that is the diffusion of the chemical is so much faster than the dynamics, whether it's like rotational dynamics or self-propulsion of particles, that we can say that in the reference frame of the particle, the concentration profile is basically steady. And so what we see is that obviously we have a sink of hydrogen peroxide near the hematite. And in the far field, thanks to Gauss theorem, we recover an isotropic concentration profile. But in the near field, we see that our concentration profile is getting the hexapolar symmetry of the microgears. And so now if we put a test particle near the microgear, and this particle is sensitive to diffusiophoresis, we can say that, to make it simple, let's replace this 2D microgear by a 1D oscillation of concentration. So as a result of the rotation of the microgear, this oscillation of concentration would just travel. So you would get a traveling wave. Imagine we put a tracer particle, a test particle in this traveling wave of concentration, and we say that this particle is exhibiting diffusiophoresis, and therefore it's moving with a mobility alpha along the gradient of the concentration. So we can say that the displacement of this particle, the position x, is going to be alpha gradient of c, with c given by a traveling wave. And what we get is that the phase of the system is going to be in a potential, which is a washboard potential. And so it's V psi plus epsilon cup psi. So we see there's two solutions, that if the washboard potential is not very slanted, which is that situation, then the particle will just fall down in this potential and stay there. You're in the synchronized state. On the other end, if you have like low coupling, so V over epsilon is small, then the particle would just like fall down this corrugated path, and that's what we observe for co-rotation. So that was kind of the hand-wavy argument to explain you what was happening and how we could account for how it accounts for the gear-like behavior we observe. But we can actually write down the full Langevin equation for the motion and predict what was going to be the probability distribution for the phase lag. So the dots here are the experiment, and the dashed line is our prediction with only one fitting parameter. So it captures our experiments very well, knowing that all the other parameters, like the amplitude of the active noise or the speed of the rotation, are measured independently. So we really have only one fitting parameter. And so with that, I will move on very quickly to a last quick bit, which is like, how can we build a machine of machines? So I've just shown you how we could make some self-assembly. So, oops, sorry. I've just shown you how we could get those particles to self-assemble autonomously by just like trigger the self-assembly using light patterns, but we don't address particles one by one. Now I'm going to show you how we can actually template the self-assembly using light patterns to build an assembly line to make whatever particles we want. And so we can do that by using the orientation of those particles in light profiles. And so here, for example, using a patterns, oops, sorry. Using the fact that if we put those active particles in a red light, then they tend to align along the axis of along the optical axis of the trapping. Sorry, there's an issue with my slide. So if you take those particles and try to trap them, you cannot trap them because hematite is scattering red light. And so in the absence of hydrogen peroxide, you cannot trap those particles by conventional optical trapping. On the other hand, now if you put hydrogen peroxide, those particles will be oriented by the optical trap. And so the scattering will orient them and the swimming will make them swim downwards. And so we can trap active particles using light patterns and a combination of activity and optical trapping that we would not be able to do in the absence of optical trapping. And so we can make light patterns and form whatever structure we want and then release the traps and the structure is going to move. And so we can make the particle go one way. We can also control the amplitude. So that's another example here where we write UCSD. So you see that we have those active particles, they run around and then we put a template and the particle will occupy the different position of our optical trap and we can make whatever structure we want. And then when we release the trap, here they would break down, but if we form the stable machine will remain. And using those kind of tricks, we can also get controls of the chirality of the self-spinning microgear using optical vortices. So in the self-assembly approach, we had zero control on the chirality. Now we have full control. We can get them to spin one way or the other. And from that, we can even build, oops, sorry. From that, we can even build hybrid machines. So a bunch of microgears where the core particle is a passive bead and the peripheral particles are active ones. And so we can make microgears of different sizes with different number of teeth and study their collective behavior with a purpose of like getting into like chiral fluids where each one of the building block has a chirality we can control. And with that, I apologize for running slightly out of time. And I thank you for your attention. So the work I presented was, the first part was the work by Sophie and Etienne, who is now at LADIX and CNRS. And the second part, the synchronization was the work of Antoine Aubray, who was a postdoc in the lab. And the last part with the templated assembly and the different type of rotors was a joint effort of Antoine and Quentin. Thank you.
Yes, thank you very much for speaking. Really impressive stuff. So I will open up for questions if anyone has anything.
I have a quick question about the first part of the talk.
Mm-hmm.
You mentioned that the ground state remains a complete crystal, even with the active particles in there, they just get you there faster. Presumably that depends on how many or how high the V0 is.
Yes. So what I'm saying here is in the limit of, I would say, doping. So we didn't go beyond 1 or 2%. Like, I mean, if you start to say 50-50 or 20,
yeah.
Yeah, it's more like a doping way of seeing it than, so we don't actually have a, yeah, I mean, at some point you would get the result that you had where you have a phase separation by motility. And I don't know how this interplay comes out. We didn't look at it numerically, and experimentally we didn't.
There's a question from the audience about how many traps you can use to manipulate these particles at the same time.
The traps part, so we're using something called a SLM, Spatial Light Modulator. So it's basically a projector for a laser. So we can, how many traps depend on what is the power of your laser. So we use a 1 watt laser and we can do maybe 20-ish, 20 to 50 traps. Then we run into trouble. So for example, that slide, I don't know, do you see the slide?
Yes.
Yeah. The movie at the bottom means that we could do at once 7 times 7 gears, each one made of 7 particles. So this one was made with 49 traps. And that's kind of the upper limit. So in order to do a chiral fluid, what we're going to do is repeat the sequence. We're going to do 7, set them on the side, 7, set them on the side. But now the making is pretty fast. So the idea is maybe 5 or 10 minutes of repetition and hope that 50 or 100 is enough to start seeing interesting features.
Okay, thanks.
Does anyone else have any questions for Jeremy?
Hi, Jeremy. Seth here from my front porch office that I'm getting used to. Yeah, I was interested about this chemical synchronization. I didn't quite follow all the details of that. Have you published anything on the chemical synchronization?
Yeah, so chemical synchronization, it's published work. So I mean, in a nutshell, like the idea is that this particle, like each one of the building blocks is consuming fuel. So if you look at the concentration profile in the near field, it's gonna have the symmetry of your microgears.
Yeah.
And so now if you look here, you have like a corrugated concentration profile, if you like. So that's this. And because it's rotating, you could say that you have a traveling wave of concentration. And so if you're a particle which is phoretic, you depending on the sign of your phoresis, you always want to be at the top or at the bottom of the concentration. And so if you slow enough, you stay at the bottom. And so it means that you will be able to synchronize. You will be able to co-rotate. And so you can tune that. So, but yeah, it's published. Antoine published a paper in Nature Physics in 2018. And there's another paper in Soft Matter, also by Antoine, which look at that. And we could actually image. We use like some fancy optical techniques called ILO to actually measure the interaction profile. So we could actually get a version of that by using phoresis to get a proxy of the concentration. There is one caveat to that, which is really painful experimentally, is that because the concentration profile is given by the symmetry of your object, your C theta, the gradient along theta of the concentration, is going to get the concentration as the symmetry of your source. So it means that if you have something which is hexapolar, the angular part decays like 1 over r to the 6. 1 over r to the n plus 1, and the gradient goes 1 over r to the n plus 2.
Yeah.
So here,
what about the rotation rate? What rotation rate did these objects have?
So the rotation rate, so that's a good point. So you will see in the paper, we very dismissively discuss that we are not quite there. So we capture the synchronization very well. The rotation rate we observe is not quite the one we would predict from that picture by a factor of 10. We are 1 order of magnitude off, and we suspect it's hydrodynamics. So I can tell you that, that work in progress I didn't present, because I think it was, but we did quite a bit of work to try to get what was hydrodynamics and what was phoresis. And to do so, we developed particle with like a polymer brush. And so now we have basically 2 sets of colloids which are identical, besides one has a polymer brush and one doesn't have it. And so one has they're identical for hydrodynamics, but different for diffusiophoresis. And so we do like basically linear combination so that we can see what is what, and that works. But it's a pain. And what you're measuring is small. I mean, it's like 1 over r to the 8 decay. My recollection is we got more like a decay like 1 over r to the 3 or 4 for the correlation, and we don't know why. So we actually, about that question, there's a figure in the paper, the last figure of the paper is just discussing it. We didn't look for pairs of swimmers. What we did was more or less this experiment, as you can see here, which was even more painful at that time because we didn't have control of the chirality. We made a bunch, we sorted out so we would have 7 co-rotating, and we could vary the relative distance from the center, and we see that the crown is co-rotating, and we measure the co-rotation speed of the crown as a function of the distance to the center, and we have a decay which is way, way, way less than what we predict.
Yeah, well, that's good because otherwise you would never observe it. So
yes. The synchronization, we still observe it, and it's decaying 1 over r to the 8.
Okay.
So we can observe it.
Yeah. All right. Well, congratulations. Yeah, that's pretty cool. That whole chemical synchronization. I would have expected things to wash out and average out with the rotation and.
One thing on this line, and it's like something we're finishing, like we are wrapping up, so it should be submitted soon, is we actually try to alleviate the fact that it's set by the hexapolar order. So we did stuff where we had just clocks. So it's one swimmer running around one colloid. And so then it's monopolar. And then we can see much longer range interaction. And we basically look at synchronization of clocks at microscale and phase slips. So basically like the equivalent of experiments that people would do with 2 flagellas, with 2 clocks which are independent, 2 phase-free oscillators, which are coupled by chemistry, which is a weird take on the stuff you've done with chemical oscillators.
No, it's related. I understand. Yeah, cool. All right, well, thank you. And we had Akif Tezkan speak a few weeks ago in our seminar, and he mentioned that San Diego received a MRSEC for the first time this year.
That's not, so yeah, but it's 100% not us.
Yes, but maybe you'll get a seed or you'll move into it.
I hope, but there's 0 physicists in the MRSEC.
Yeah.
Unfortunately.
So just become a chemist, that's all.
Yeah, I'm fine with that, or an engineer.
An engineer.
It's always fine for me.
I mean, this is engineering, what you're showing right here.
I have no problem with engineering.
Yeah.
All
right, well, thank you, Jeremy. Thanks a lot for participating.
Thanks for the great talk. See everyone at the next Brandeis MRSEC seminar.
Thank you. Thank you. Bye-bye.
Bye.